Hello kids, today we are going to talk about error. So we are at the end of our series unit where the big idea that we've been working with is having a function on some interval. The best interval, of course, is negative infinity to infinity. But if we can't get negative infinity around the center, let's just for emphasis, for simplicity's sake, say our center is 0. Right? Maybe this is negative 1 to 1, negative 2 to 2, whatever it is. Again, ideal would be negative infinity to infinity. But we have some function in here. And we can build an infinite series. And an infinite series will match that function at the center. And then it will, as you radiate to the right and the left, it will match the function exactly as long as you are infinite. But if you truncate, right, and cut off, it will only match it for a certain number of terms within that integral. Right, and I purposely made that not balanced, right? It started to diverge earlier on the right side than on the left. So what we want to do is be able to talk about, well, let's pretend that the p of x, the yellow p of x, right, approximates f of x. So if, for instance, I have an x right here. Let's pretend this is 0.5. If I go up to my function and I plug 0.5, f of 0.5 is going to be approximately my truncated polynomial. Maybe I cut it off after 2 terms, maybe 4 terms, maybe 3 terms, whatever. My polynomial at 0.5 equals some number, and I want to know how bad this number is. How far off is this? What is the error in using p sub n of x to approximate? We have 2 error bounds. So oftentimes finding the exact error, not really doable. But if I can say, well, your max error in using the polynomial will be 0.005. That's pretty good, right? That's the maximum. I'm not saying your error will be 0.005, but what if the most it can be is 0.005? That's nice to know. So we have Taylor's theorem that goes with the Lagrange error bound. This one is harder than the alternating series estimation theorem, which also gives me a maximum bound for my error. And it is mathematically easier, but of course, guess what? You can only use the alternating series estimation theorem if you have an alternating series. Okay, so Lagrange will always work, but it's nastier than if you can just use the alternating. So lesson learned. If AP asks me to do an error analysis or find an error bound, the first thing I say is, oh, please, please, please let the series be alternating. If the series is alternating, boom, I got very little math to do. If the series is not alternating, rats. So I'm going to do the Lagrange one first. So here's an example of a problem. Use the 4th order, so that's p sub 4, Taylor series for e to the negative 2x, centered at 0, and use it to approximate for x a value pretty close to the center, right? 0.2 is pretty close to 0, the center. And I want to know what's the error in my approximation. So the first thing I have to do is build the series. e to the negative 2x is approximately, fourth order means go to the fourth derivative, and I built my series knowing that e to the x was 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and I composed negative 2x in there. I used my calculator. I put this into y1, and then I asked the calculator, right, what my function was. I said y1 at 0.2, and I got this number. How close is this not infinite, this truncated polynomial? How close is this number to e to the negative 2 times 0.2? Well, I have a calculator, so I can figure that out. So in my calculator, instead of putting 0.2 into my polynomial for x, I just put I did on my calculator, right? E to the negative 2 times 0.2, and look what I got. This approximator was good to 3 places past the decimal. Pretty freaking close. How close, you say? Well, just take your fact minus your fiction. Absolute value, because I don't really care whether it's, and the sign would just tell me too high or too low, right? So using the fourth order Taylor series for e to the negative 2x, which is what your calculator is doing to get these numbers, my actual error, not an error bound, this is my actual error, is what? 7.9 times 10 to the 1, 2, 3, 4, 5. Did I do my scientific notation right? That's pretty good, right? That's pretty good. That is an acceptable, right? For most things, I would think that is an acceptable margin of error. And all I'm doing is plugging numbers into a fourth degree polynomial. Pretty cool. Now, instead of actually calculating the error, though, what I would like to be able to do is find out, well, what's the worst case scenario? What's the maximum error in using p sub 4? I don't actually want to compute, right? I want to say for, right, around my center, what's the worst case scenario? So here's where Taylor's theorem with remainder is. Here's Taylor's theorem right here, right? All the way to, right, the first derivative, x to the first over 1 factorial, second derivative, x to the second over 2 factorial, to the nth derivative over n factorial, x minus the center to the n, plus all the rest. This r sub n is the remainder, but all it is, and I want you to think about having like a suitcase or a travel bag, and you're packing all the rest of the terms into here. And if you could add them all together, you'd get the remainder. So remember, f of x is exactly equal to this infinite polynomial, not approximate, equal to. And all I've done here, I haven't truncated, I've just packed all the rest of the terms into this box and called it the remainder sub whatever I cut off. Okay, so let's say when I approximated, right, when I used p sub 4, my remainder sub 4 would be all the rest, the fifth derivative, sixth, seventh, eighth, all the way to infinity. If I could add them all together and pack them all up into one term, add them all up into one term, I'd call that r sub 4. So look at how this remainder term is defined. It is the next derivative over the next factorial times x minus the center raised to the next power. You are used to seeing the derivative there evaluated at the center. We can't evaluate it at the center anymore. All we can say is that there is some c between the center and your x that you're predicting, that your remainder will be equal, right? Will be equal to all the infinite terms that are left packed into a box. That's powerful. That Brooke, he did a great job. He proved that. So the remainder of order n is kind of a mouthful to say. Lagrange did a bunch of work with it, and so that's why it is called the Lagrange form of the remainder. I've seen Lagrange with a lowercase g and a capital G there. I think in France it would be capital G. The maximum value of this remainder is called the Lagrange error bound. We can't find this c that would give us the exact value of the remainder, but we can tell you through the work of Taylor and Lagrange what the worst case would be. So note that the remainder piece, the remainder term, looks just like the next term after you've truncated. Evaluated, though, at some domain value c, which is not your center. This theorem guarantees the existence of this c value, and it is built from the mean value theorem. That's kind of crazy. All right, so here we go. The Lagrange error bound. I forget Lagrange's first name, darn it. If there is a positive constant m, and notice this m is red and this m is white because they're different. If there are a positive constant m such that the absolute value of the next derivative, I don't know why I used t there and not x, is less than or equal to some number, then it will be true that your remainder term, which is the sum of all of the terms after you truncated, is guaranteed to be less than or equal to some numerator over n plus 1 factorial. And again, these are absolute value bars here because I don't care whether I go to the left or right of the center. Evaluated at the next derivative. The next power. Remember, A is the point of tangency or the center of the expansion. X is the value that you want to approximate. So remember in our example, I wanted to approximate e to the negative 2x at 0.2. Our book uses a slightly different formula, but I like this version better. So here I am with my previous example. F of x was equal to e to the negative 2x. I approximated e to the negative 2x with the fourth order polynomial. I wrote out my fourth order polynomial and I stopped it. It is truncated. I plugged in 0.2 and I got this value. The error bound gives me the worst kind of error. The worst my error will ever be using the fourth order polynomial to approximate any x value from 0 to 0.2, right? And 0.2, remember, is my chosen x. I can use anything in here. And the worst error I will be is this expression. Notice the white m morphed into a 32. I don't want you to worry about that yet. I want you to just look at the remainder term. For me was, right, since I used, this would be r sub 4 of x. Is less than or equal to this expression where, since I had r of 4, my remainder after the fourth order was 4 plus 1 or 5 factorial. X minus a was, right? X is the number I'm trying to approximate. So that was 0.2 minus my center was 0. raised to the n plus 1, 4 plus 1, which is 5. So if you did 32 over 5 factorial times 0.2 to the 5th, you would get this number. This number is the Lagrange error bound. It is the worst error you could get using any number between 0 and 0.2. So the only thing is, where did that freaking M32 come from? The white M, this 32, is the maximum of the next derivative. So this was this what makes Lagrange kind of annoying. I had to take my function, e to the negative 2x, and I had to find the first derivative, the second derivative, the third derivative, the fourth derivative, and the fifth derivative. So I had to find the fifth derivative. I then had to take its absolute value. I just put this in y1 in my calculator, and I graphed it on 0 to 0.2. And it looked like this. Where that maximum was at 32. That's where the 32 came from. This is the annoying piece of Lagrange. Oftentimes what AP will do is give you that number, right? They don't really want you, they will test you plenty on finding derivatives. They'll give you this number, but you have to know Lagrange's formula. Now I want you to look at what I got here. 1, 2, 3, 4, 8. That number is bigger or smaller than 1, 2, 3, 4, 7. This is the maximum error using P sub 4 for any x from my center to the approximate, to the number they were asking me to approximate. And sure enough, when I tested with 0.2, which is the worst case, right, all the way the right end, I got an error that was less than my Lagrange error bound. Crazy. So let's do another example from scratch. Find the maximum error when x minus x squared over 2 is used to approximate the given function. This is my approximator. What order is it? Can you tell? 2, right? Can you tell it's the second order? Right? Because I have a squared over 2, so it means that the coefficient of the x to the first term must have been 0, right? What is this? The x's, instead of giving me just a 0.2, they're asking me about any x between negative 0.1 and 0.1. That's what that says. So I want to know what is the maximum error. So that's going to be my remainder, since I've got P sub 2 of x, the remainder after the second order is less than or equal to m over n plus 1 factorial times the absolute value of the x they want me to approximate. What x do they want me to approximate? They want a whole bunch of them. Which ones are the furthest from the center? Negative 0.1 or 0.1. I'm doing absolute value, so I might as well put 0.1 in there. Raised to what power? The n plus 1. Here's your n. So my job now is to find my m, that white m. That m is the maximum of the next derivative evaluated at some c that I don't know, but I'm just going to look at the function, the third derivative, and look at it on the interval that I'm asked to approximate with. So that means I have to find the first derivative. One over 1 plus x times the derivative of the inside, which thank goodness is just 1. This is 1 plus x to the negative 1, so when I take its derivative, it is negative 1. 1 plus x to the negative 2, which means I'm in the denominator squared, times 1. And the third derivative, oops, sorry. I'm going to bring down a negative 2, multiply times that negative 1, so I'm going to get a positive 2 times the derivative of 1 plus x, which is just 1, and I can stop, right? So I need to take this function up here, use your calculator, make your window negative 0.1 to 0.1, and look at the max. Don't forget you're taking the absolute value of that. So it's going to look like this. So the right endpoint is the maximum, and I used my calculator to find that value. And I got m to be, I wrote it down somewhere, where was it? 2.7438. I just stored that. I really just wrote down 2.7 when I was writing. So I put it in my calculator real quick. I stored that in alpha m. And then I put that number here. So I did alpha m divided by 6 times 0.1 cubed. And I got out of that which is a pretty freaking small number. So the worst error I could have in using this freaking upside down parabola, right? That's negative 1/2 x squared plus x, to approximate this natural log function for any x between negative 0.1 and 0.1, the worst error I'm going to have is 0.000457, which means anywhere else, right? Any other, and that, because that was at the either endpoint, my error is actually going to be less than that. That's pretty good. This is the Lagrange error bound, this number, for using this second order polynomial to approximate this natural log function. Crazy. All right. So What order am I using? I computed the first 3 derivatives then because it was the second order. I found the maximum of the absolute value of this third derivative. I used my calculator to do that. To find that left endpoint. So that's what I got. Right? Instead of using my I just you see what I did? I plugged into here. Negative 0.1 or 0.1, it doesn't really matter. And then I computed the error. Pretty cool. Again, I could have used it was equidistance from my center to 0, negative 0.1 or 0.1, which is why I used there. Or I could just put this into y1, either way, right? y1 and look at the graph. Or I could have, again, for x, plugged in the value to the derivative, knowing that it was the left endpoint, since the function constantly decreased. The absolute value of the function constantly decreased. Now, let's look at the actual error. So I plugged in because, I was equidistant from my positive 0.1 and my negative 0.1. I plugged both of those into the function. I plugged both of those into the parabola, subtracted them, and look at my error. Both of those actual errors were less than my Lagrange error bound. Now, one more example I'm going to do with you. Tricky problems like homework, like number 19 in your homework. I kind of think this is unfair when you're first learning it. So I do want to highlight the way they asked this problem, though. I think this is a convenient way that they word things. They're giving you a function cosine x. So there's my f of x. They're giving me an approximator, right, which is a second order. They want the error magnitude, just means the absolute value, to be no greater than 0.0026. So what they're saying there is that r sub n of x is less than or equal to .0026. So with this being a second order, you would think that you should plug in 2 there, 2 there, 2 there. And remember, they want you to solve for the x. So you are going to be, in this case, looking for this x. But right, you're going to solve for it because you're going to be less than or equal to 0.0026. Here's the trick with this problem. Think about what you know with cosine and the series for cosine. What is the next term? Not the next non-zero term. The next term. Can't I just as easily claim that I'm using the third order polynomial for cosine? That's cheesy, but that's what, and I've not seen AP do this, but one of your textbook problems does it, so I wanted to highlight it. It is true that p sub 3 of x is equal to p sub 2 of x, right? The third order polynomial is equal to the third order polynomial for cosine. Truth? Truth. So I make a stronger statement by saying I've used a third order approximator. So I'm going to fill all these ends in with 3. So I'm going to erase what I have here because I didn't leave myself enough room. So r sub 3 of x is less than or equal to an m divided by 3 plus 1 factorial times x, and my center is 0, to the 3 plus 1. And that needs to be less than or equal to 0.0026. Where am I going to get that m? Here's another little cheat. Talk to me about cosine. Don't really care about what interval I'm talking about, right? What is cosine? Remember, we're talking about an error bound. So I'm talking worst case scenario. So if I fudge a little bit on that m, what if I just tell you that the worst case scenario for cosine is that what's its maximum value no matter where you are for cosine? What's the maximum value? 1, right? And the derivatives are signs and then negative signs and the maximum of all of them is a 1. So I'm just going to make this a 1. Right? Just saying that rather than computing all the derivatives and looking on the interval, right? They haven't given me an interval. So I'm just saying, hey, the worst I know I can be for sines and cosines is 1 anyway. So I'm going to make the maximum of the next whatever derivative is going to be a 1. And now I just am solving this inequality for x. Multiply both sides by 4 factorial. So what x's can I use to make sure that my error is no greater than 0.0026? Right? Pick any x's in between there, plug into this parabola, upside down parabola, and approximate cosine. And if you use any x between here, your error is guaranteed to be less than 0.0026. Woot, woot. All right, so that's Lagrange, and I even gave it a Lagrange tricky. So you can see that even though I kind of I was like, oh, let me kind of cheat and call this p sub 3, and then let me kind of not actually find derivatives and calculate the max of the absolute value of the derivative, blah, blah, blah. I'm just going to sines and cosines, so I'm just going to say that max is 1. It still was a kind of a messy problem, which is why if you have an alternating series, oops, forgot that I wrote all that, typed all that up. You want to use the ASET, alternating series estimation theorem. As long as you have a convergent alternating power series, the maximum error from using a cutoff polynomial to approximate a given function at any x within the interval of convergence is just the value of the first unused term. What? What? So, for example, given this series here, it is alternating. It is a power series. I want you to use the alternating series estimation theorem to determine the maximum error if you use the first 4 non-zero terms to estimate the function at point 1. So there's my series. Write out the first 4 non-zero terms. Right, I put a 1 in here. 1/1 negative x squared over 2. Sorry, x to the first over 1, x squared over 2, yada, yada, yada. Alternate your signs. These are the first 4, 1, 2, 3, 4 non-zero terms. This is a truncated polynomial. So I am approximating a function. So the function at point 1 will be approximately the polynomial at point 1. So I use my calculator and I put point 1 here, 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 and here. And that's the number I got. What is the error in this number? Because it is not exactly the function at point 1. What is the error? The error in using this will be the polynomial to approximate will be no more. The worst error you can have is the next term, the value of the next term. So I use the 4th order. So the next term is 0.1 to the 5th divided by 4 plus 1, which is 0.00002. Right? That's pretty freaking good. Pretty freaking good. So if you think about this, right, in the last video we talked about right, the idea of conditional and absolute convergence. Well, the reason with an alternating series, the worst error you can have is the value of the next term, because everything after that, you're going to add a smaller number, but then subtract a smaller number, add a smaller even number, subtract, right? So the next term is, its magnitude is the biggest error, the biggest error that you could possibly have in using the truncated polynomial. Love A set. Much better than Lagrange, right? And this was Leibniz. That's Leibniz up there. He came up with the alternating series estimation theorem. I like Leibniz way better than I like Lagrange. So if you are asked about an error bound, the first thing you see is please, please, please let it be an alternating series. If it's an alternating series, I just have to plug the number that I'm asked to approximate into the next or the first unused term. Boom, there's my A set error bound. If it is not an alternating series, I got to go Lagrange. All right, and we'll practice some more of that in our next live session.